I'm Scott Lathrop at the National Center for Supercomputing Applications at the University of Illinois, and I want to welcome you to today's Blue Waters webinar on Kepler Scientific Workflow System, an introduction to workflow-driven scientific computing. And it's our honor and pleasure to introduce our two speakers today, Ilkay Altintas and Shweta Purawat. They'll be providing the content today. Ilkay is the Chief Data Science Officer at the San Diego Supercomputer Center, and Shweta is the Data Science Workflow Specialist at the San Diego Supercomputer Center. Their bios are on the webpage there if you want more information about their background. It's really our pleasure today to welcome them to talk about Kepler. And with that, we'll start with Ilkay. Please take it away, Ilkay.
Thank you, Scott, for the kind introduction. Good morning, everyone. I'll talk in the first half of the seminar on Kepler workflow system and in general scientific workflows and how they are being used today. Then we'll switch to a demo session on Kepler, hoping you would stick around for that. So why do we have workflows even today, and why are they becoming more useful, right? Because today's computing is changing. It's a lot more heterogeneous, and it's a lot of tools getting together, and our ability to measure our environment, measure everything is changing. And the influence of big data is also affecting the way science is being done. So it's becoming more dynamic, and a lot of these applications that are traditionally supercomputing or high-performance computing, high-throughput computing applications are also becoming dynamic big data applications. All of this put together, we can't do things step by step anymore. We need to really coordinate at a higher level. And I think what we started as a community with workflows are becoming a big solution for that. In terms of providing software coordination in a dynamic fashion as much as the big data needs it or the data analytic steps needed, and also resource optimization, responding to the heterogeneous computing challenges of these applications. What do I mean by that? We actually do that in everyday science, not in computing. We did not do this in computing earlier as much. Even when we cook, we want to make pasta this evening. We get our ingredients, and when we are making that, dynamically things happen, right? We adjust to that. A good cook would know they need to shop for 30 minutes. Maybe they need to leave 30 minutes to make the pasta sauce. We can also open a can, I guess. And 15 minutes into making the pasta sauce, which takes 30 minutes, if we boil the pasta and make sure it's ready by the time the sauce cooks, it's actually easier to quickly mix it, and we don't lose time in terms of the end product. So it's actually, there's a little bit of optimization here, right? The overlay sauce making and pasta boiling steps. And then later on, we can, of course, store things or eat and things like that. There are different steps there. So workflows do exactly this for science, or they need to step up to doing exactly this. And in real life with cooks, it takes a lot of exploring to really get to that understanding that, okay, the sauce pretty much takes 30 minutes and the pasta boiling takes 15 minutes, or different sauces will get different times, or even oven capacity or kitchen capacity will take different times. And in fact, there's a book called How to Cook Everything Fast that does exactly that. Right? It tells you how to take advantage of the idle time when you're cooking. When the soup is boiling, maybe toast your croutons or whisk your dressing for a salad and things like that. So this happens in real life, and it happens in a number of different places. What if there are multiple cooks? Then let's say we are making pasta sauce together again, and you have a bunch of vegetables, and maybe you have 3 friends over. You're giving them a batch of vegetables each, and they'll start get the cutting, right? This is very much like the map operation. If they cut everything and make different batches of different vegetables. So it's a divide and conquer or map reduce style, in a way, computing or process. And then they'll have to, when you want to bring them together, it's like a reduce operation based on the vegetable type. You would put all these vegetables together and later on move into cooking steps. So when I look at this, I see this cooking example very much like how we do things in the big data world and combine it with the high throughput, high performance computing applications. Then you have that big data load that you can chop and prepare for analysis. It's very much like data parallel computing. And once you've prepared maybe the analytical results to be inputs for yet another computation that might require a high performance computing resource, then executing that application will have yet another semantic in terms of how we need to execute that, and how much data you would have and how much data you would send to the computational application, or how much data comes out of a simulation or other high performance application also relates, right? Then you can take those results and apply big data techniques or in situ workflow techniques these days to really quickly process that data, post-process, pre-process data based on the data load and the resource availability. So this is like our reduce. But workflows are not just map reduce or high performance computing, as I mentioned. It's almost like a Thanksgiving dinner, what I described to me. There are different meals. They take different times. They have different preparation times, cooking times, cooling times. This is like preparation, post-preparation, and analysis. And there are lots of other things to consider for planning and tasks. When do you start cooking? What order you cook? Do you cook maybe the pie earlier because it needs a day to cool down and maybe taste better? Things like that. And who cooks what? If you have multiple people making the dinner, how are you going to use the kitchen resources to respond to what they need when they need? So I think these aspects of workflows will be more and more useful in terms of resource optimization and planning of tasks and resources, coordination of tasks and resources as we go along. Because today's workflows are exactly like, to me, a Thanksgiving meal. It's very heterogeneous and it has many steps. And over time, we can learn about these applications to make it useful. I don't have to cook the same soup always for the Thanksgiving dinner, but me understanding what the soup needs will affect my decision. Similarly, if we can approach workflows, not just as a composite activity, but as a composite activity that is composed out of modules that we can learn about, even if we are running a workflow the first time, if we know what the modules is running on the computing resources we have, we can actually achieve better performance in a dynamic data-driven way. But this will require changes in the way we do computing, in the way we build our computing resources, in the way we build our workflows, in the way we build our, in general, computational components. So how does a Thanksgiving workflow look in that sense? It definitely has data access and management layers, which we could bundle as staging and pre-processing, analysis components where we really, it's almost like you put the chopped vegetables in and you get pasta sauce out. What you get isn't a veggie anymore. It's transformed. You have something useful out of your data. And then the reporting steps that includes post-processing and really, again, dynamic data-driven management of the data coming out of the weak simulation or analysis steps. So the first half of this, and actually the second half with the reporting, I would see this as a big data engineering and computing for management of that data. And somewhere in the middle to end, it's not as strict as I describe it maybe. It becomes this computational big data science. So we can't distinguish, or we shouldn't distinguish so much about what's HPC, what's HTC, high throughput computing, or what's a big data analytics computing. I think it all comes together in the most successful applications these days. That's one way of looking at the process. We could also look at the human side of it, or how the science gets conducted side of it. There we can start with this build, explore, scale cycle, right? Somebody needs to build workflows, and it generally, even if you build a small workflow, there is some exploration with it. You try to get it right. It's almost like building a recipe to analyze something, or analyze, cook more data. But if after that exploratory step, we need to, and it's generally the practice, scale it up. So whatever we build in the name of workflows should have support in terms of reproducibility and communication of all these different steps. And we see a lot of applications in different domains. That's what I meant with XXX here. Replace your favorite domain with XXX there, application domain. The goal here is to facilitate and accelerate data science and computational research. So important attributes of these is how can we assemble processing, complex processing easily, and how can we cut the loop to access to the diverse resources based on what that assembly looks like and how that assembly reacts to data, and how that assembly actually incorporates multiple software tools and adjusts the availability of the data and resources based on what these tools need. And at the same time, we need to issue reproducibility and robustness, and science is very collaborative, so it really needs to respond to that collaborative aspects of science and build around the community development model. How is this in biological sciences? As you see, the way I see it is there's data in the beginning and end of the scientific cycle. You acquire data, you generate data, and then there's the data analysis step and data publication and archival in the end. So we can actually go through any of these loops. Maybe we start sometimes with data analysis. That's a form of acquisition if we run a big model or simulation. But at the end, we need to go from the data we start with, that might come from sequencers, sensor networks, medical imaging facilities, you name it, IoT devices these days. And we analyze it in a way that is data intensive, HPC, big data, local exploratory, that heterogeneous activity. And then we make the results analyzable and searchable. That requires standardization, modeling of the workflow, integrating to data systems or data models. It can even lead to auto-generation of methods and materials. We don't have to go back anymore if we capture the activity well to rewrite those methods and materials, because if the process captures what it's doing, it's a very queryable and achievable bit to write an automated methods and materials section for our papers if it's archived in a community open platform. Of course, we can even use workflows, and we have been using Kepler workflows just to cut that data to archival cycle. So it can be generally done in real time, especially the data is being produced consistently, continuously over time. And while doing that, can we do some data cleaning, QA and QC on data, quality assurance and control on data, especially data coming from sensors, and reduce the data so it's going to be useful later on for analytical applications. So this aspect of workflows are good. Of course, we are coordinating the data to the analysis to archival bits. So in that sense, I think their biggest use comes from fostering collaborations. When we are doing this, it becomes this shareable, archivable entity that collaborators can collectively work on. And other advantages that comes is it brings some flexibility and synergy to optimize resources, and each of the steps can be standardized and increased reuse, and also overall workflow itself becomes a publishable entity. So since early 2000s, I should say, workflow systems have been built, especially thanks to the grid computing, making resources, distributed resources available. And they are being used as a part of the scientific cyber infrastructure to support this end-to-end computational cycle today. They are actually in more places than we all know, because a lot of the times they run in the background, and the scientific community has successfully embraced a number of different workflow systems. And in generally, they get built, they get shared through a cyber infrastructure or a gateway facility, and they run in the background to coordinate scheduling, execution planning, monitoring of that execution. And since they save data on that run in terms of provenance, later on we can use those bits to learn about the activity and bring more reproducibility and create run reviews and analysis over the previous runs. So this is actually more standard practice than we acknowledge, in my opinion, at times. And part of these workflow systems is graphical workflow systems. They have these graphical components by drag and drop of reusable components that relates to data, compute network, fault tolerance, you name it. You can create workflows and run them in the engines that environment provides, often not in that environment, but in batch as well. But they're not Microsoft Word. They need a little bit of expertise to identify which tool to need when. That's the requirement and the knowledge of the breadth of that computational activity and the technologies available to use in terms of different depths related in each step of the activity. And they also require computational models that need to evolve to schedule and optimize the execution in a dynamic data-driven way. Kepler is one of them. It was initiated August 2003. It's an active project. It's a very mature active project. Our release cycles are more, our last release was in 2015. There are frequent module releases. There are incremental releases within those. This is our website, and it builds upon even a more mature framework, a very expressive framework that was built for engineering simulations before, called Ptolemy 2. So Ptolemy 2 was for engineering simulations, and when we saw that the expressibility of it to use different modes of computation was really attractive to building scientific workflows, because we expected that this heterogeneous bit in terms of exploratory HPC, HTC workflows will grow and will need new computation models. Maybe each part of the workflow will need a new computation model that we can compose into an overall activity. So we call, in that sense, Kepler Ptolemy plus X for scientific workflows, because of that bit that we use that expressive background, but we added a lot of tools into it that can be useful for scientific computing. It's been used in many different domains, more than 100,000 downloads to date in terms of its software adoption. And these domains are ranging from physics to computational chemistry to metagenomics to environmental sensing, and many other application areas in even municipal applications and data science applications that related to metro scale studies. What does a Kepler workflow look like? It's the graphical environment consists of a panel that you can pick components, search for data and other computational components, and drop into a canvas that you can then click these workflows, link these workflows together. Workflows components are called actors, these green blocks you see here, and they have input and output ports. And to an actor, it's very separated from the rest of the workflow. An actor itself would only know, just like a parametric function, after being configured through its parameters, it takes a set of x's and produces a set of y's. So it's like a function that has some inputs and outputs, and it only knows what to do about its own function. And directors that implement those computational models, they can be dynamic data-driven, they could be static, synchronous data flows, they could be continuous time models like we see in this example, coordinates how actors pass information to each other and overall how the overall graph gets scheduled. So that link between the actors, what that means is defined by a director. Sometimes data passes through them, sometimes messages can pass through them, and things like that. Or sometimes the schedule is based on a clock tick or an event being there to trigger the execution of the next activity. So another Kepler workflow here, we can see the typical operations in workflows. Data flow is divided, and actors will perform the tasks. And workflow parameters to interact with the workflow later can be also conceptually spelled out and put in as executable parameters in there. Once we have this workflow, it gets saved as a graph definition, and it can be run in batch mode in any computing environment. You can run it, of course, through the user interface, but most of the time workflows take a long time, and the way it's used is either behind gateway applications or through a supercomputing facility, like we'll show today. Actors also can come in different types. There are input actors that don't have inputs themselves. They just produce some values for others to, or access some data resource. And there are also nested workflows that conceptually brings together a sub-workflow, a graph, like an actor. So thanks to that actually nesting, in these nested, we call them composite actors, in these nested workflows, you can have different computational models. And we have some papers on how you can bring together these different computational models and compose them as one workflow without breaking the laws of computability and things like that, if anyone's interested. I'm going to quickly skip over this slide because there are very many actors in place. So at this point, when you're using Kepler, you should not need so much to add your own actors because they're just generalizable containers that can host different types of computational loads, and they can communicate to different schedulers, or locally they can even execute different analytical components like Spark, R, MATLAB, KNIME, local OpenGIS tools, and things like that. I think the one that we are going to really emphasize today is this workflow execution across multiple environments through an execution choice actor. So under one actor, you can build different ways of executing a particular computational executable. It could be locally, Hadoop, if it makes sense, or Spark. It could do a cloud environment, remote job execution on supercomputers. So this, I hope, will be more clear in the demonstration. So that one actor should give us more of a nimble execution across a set of platforms based on what resources does the user running the workflow have available to them, and also what kind of data requirements there are, what kind of other steps in the workflow. So the goal here is to optimize that interaction with systems, but not keeping the flow of the workflow out of sight. we need to know where we execute and what the next step needs from that execution. Quickly, some recent Kepler workflow applications. Right now, I think mainly the workflows that Kepler has is being used through different cyber infrastructure systems. But if you see these three architectures, what's common to them is there are workflows in the middle, and they bring together tools, computing and data facilities, and communication interfaces. Call it a gateway or a lightweight workflow, lightweight website. They are being used in the background to coordinate the activity for a set of resources. Wi-Fi is one of them. Its main goal is to bring big data, like in satellites, sensor networks, and model products and imagery related to wildfires. And based on what we have available, how many fires are happening, and things like that, coordinate monitoring, visualization, and modeling activities related to the fire. And when you're doing that, you need to take advantage of available computing resources during the fire on an on-demand fashion, before and after the fire in batch mode for planning and updating some of the databases. So this is one example of a fire modeling workflow in MyFire. There's these real-time data coming into the workflow. Also, we can do quick checks on the fire perimeter based on other real-time information and imagery. There's some static data. Execution of all of this, combining all of it with the right open GIS tools, geoinformatics tools, and fire modeling tools, and integrating and assimilating the data in real time to these modeling tools to generate predictive fire behavior models, where the fire is going, how fast, the direction of it in real time, and then communicating through a web interface these results. So it's like a web application running Kepler workflows that do all the processing of the data. So each of these actually real-time data bits are workflows themselves that feed into an overall data modeling and fire modeling workflow. You could do flexible data mining operations. This heterogeneous execution choice actor, for example, one actor in the data mining components is k-means to do clustering. You can build one actor to do k-means locally in R, KNIME, or on Spark using machine learning libraries, or Hadoop using Mahout. So we see the 5 tabs in this one actor. It's called a bioactor because this was actually initially built for BioKepler, but we are now creating a whole machine learning modules that is similar to bioactor, composed of these different machine learning tools to scale the execution of them in computing platforms. Something like this also applies the same exact approach with map and reduce components in it to Bayesian network learning. Here we have local learners implemented as maps, and master learner brings together, and the whole execution can take place on a Spark or Hadoop cluster or a Flink cluster through the communication with the Kepler's distributed data parallel director. Here we see one workflow that has a synchronous data flow director, and we also have a workflow that has in it a composite actor that has its own distributed data parallel director that can communicate the execution of this particular sub-workflow to Hadoop, Spark, or Flink as an external engine. So something like this gets used in insurance and traffic data analysis applications that can take advantage of Bayesian network learning. So it becomes also reusable and scalable at that level. Another application is scalable drug discovery. I'll quickly pass through this because of time considerations, but this is for P53 reactivation compounds to string together a set of components that do ligand parameterization, ligand simulation, and clustering, things like that, in a high throughput mode and to hundreds of thousands of applications. The benefits of this is each of these steps becomes reusable, and all of them actually were built by students. So we can build these multiple methods and compare those methods as well through these workflows, and use the workflow as a training opportunity for the students. Another thing that we'll show in the demonstration is a GPU-based molecular dynamics workbench. Here, we will show you how this workflow can take advantage of a number of different resources through that one actor that can do local and remote execution on GPU nodes or other supercomputing nodes through configuration of a few parameters. It shows the increased reuse and provenance as well. So once these workflows are built, you can, as I mentioned, generate execution reports. Another workflow that was built this way is also on the biomedical domain. The interesting bit I'd like to mention about this workflow is it's very multi-scale. There are atomic level simulations that are built as a workflow, and that workflow can then interact with also cell level and tissue level simulations. The science behind that is amazing, of course, but also I think usage of workflows in it is pretty unique because we have workflow computations that are scalable or at different scales of science from atom to cell to tissue, but also we have workflows that use different computing scales. So it's a combination of this multi-scale in terms of scientific scales, biomedical scales, and spatial and temporal, and scales of computing. It's a nice combination of three sub-workflows coming together to create this multi-scale computation. So single level, cell level, and tissue level is shown here. And again, the workflow is parameterized. And once it's built, we communicate with the workflow through those parameters shown in the bottom. And how do you then communicate to the rest of the scientific flow? How do we integrate this scientific workflows with the scientific process, how the science is being conducted and communicated? These days, Jupyter Notebooks is being used as an exploratory workflow activity. We thought of a couple of years ago, taking advantage of when it was called IPython. That's why we mentioned it as IPython on the slide, I think. But we built a magic function to create Kepler computations, to start Kepler computations through IPython notebooks. So if you can imagine if you did some exploratory analysis with the data and you're ready to spark off a scalable execution, it can go through the notebook and it could be recorded through the notebook. And the results of the workflow can be viewed through these Jupyter notebooks, as well as the provenance of that workflow can be queried and generated as a report and pasted into the notebook as a report as a part of the activity. So it fits how science is being done also, especially in things like this particular workflow, where there are so many different parameters of different scientific codes. And you need to sort of tune them and analyze the data to even start running these simulations. I'll quickly step over this because of time, but this one was a imaging facility workflow where we do tracking, alignment, reconstruction, and we have a toolkit for it. I'll update the slides with citations to publications that describe the workflows I showed today if there's any interest. To summarize, Kepler workflows, like many other workflows, are useful for documenting the process, but also ability to work across software platforms in a distributed data parallel fashion and create some reusability and reproducibility over that process. With that, I'll switch over to Shweta for the Kepler demo. I think we'll do musical chairs here and switch chairs as well.
Hello, everyone. Hope you enjoyed the first half of the session. In this session, I'm going to demonstrate Kepler interface to you. By the end of this session, you'll be familiar with Kepler interface and key functions and capabilities of Kepler. Before we move to the Kepler demo, I would like to introduce Kepler Exceed framework to you. A lot of domain scientists feel limited when it comes to scaling up their workflows. You need to have good knowledge of big data technologies like Spark, Hadoop, Flink, how to schedule your workflows on high performance computing clusters using different schedulers like Slurm, PBS, SG, how to scale up on Amazon EC2 workflow. So here Kepler comes as an abstraction layer between the users and this complex and emerging big data technologies. To simplify your task to build the workflow and scale it on all this high performance clusters like Xseed resources and Amazon EC2 cloud infrastructure. Also, if you want to learn more about this big data technologies, or you want to contribute your experience about using big data technologies in your research, you can go to biomedicalbigdata.uchd.edu. It's an e-learning platform for biomedical big data training and collaborative, where you where there are a lot of courses and trainings on different big data technologies used in different science domains. So basically, it's a happy user with the Kepler interface. Now, I'll show you how you can install Kepler on your system. Kepler requires Java 1.8 to run Kepler 2.5, which is the latest version of Kepler. You can download, Kepler supports Windows, Mac, and Linux platforms. You can download installers for Mac, Windows, and Linux-based platform from the link shown in the slide. Once you download the installer for Windows and Mac, you can click on the installer and follow the process as you do for other installers, other applications that you install. It's very simple. And for Linux, it's a tarball. You can download the tarball, untar it, and start the Kepler using kepler.sh. For the demo purpose, I have already started the Kepler. I'm sharing the useful links for different things that we have used, like Kepler downloads, the link to download the installers, then the documentation where you can get started with the Kepler, and user guide. So let's move to the Kepler interface. So when you start the Kepler interface, you'll see your landing window will look like this. The major areas of the Kepler interface window are workflow canvas, where you can drag and drop different ready-to-use Kepler components to build or edit your workflow. This is component data and outline area, which has search function and library of components that are all already included in Kepler for ready-to-use purpose. Like if you go into the component section, you can see various actors, actors clubbed into different categories, like data input actors, data operation actors, various directors that control the overall execution of the workflow. We have synchronous data flow director. If you have a data flow which is sequential, you can use synchronous data flow director. If you have some dynamic element such as decision making in your workflow, like this particular branch will execute if this condition is met, then you can use dynamic data flow director. We also have distributed data parallel director to help you with scalable workflows on Spark, Hadoop, or Flink execution engines. Apart from that, we have commonly used functions in the toolbar, such as zoom in and zoom out, and how to run a workflow. To run a workflow, you can click on this button. We'll use as I demo the workflow execution. So let's start with opening an already existing workflow. To go to the demo workflow, click on the demo folder and then expand the getting started workflows. So here you'll find sample workflows where you can get yourself familiar with the Kepler interface. Let's open an existing workflow. If you double click on the workflow name, it will open up in the workflow canvas. So this green colored boxes are actors, as already explained by Ilkay. And this is the director which controls the overall workflow. In this workflow, an array of 1 to 10 is given to the R expression actor, and it evaluates mean, standard, and variance. It's a simple R execution workflow. If you want to configure or edit R functions, you just need to double click on the actor and you can modify the functions over here or add additional functions for your experiments. To run this already existing workflow, you can click on the Run button. And the output actors will display the mean, standard, variance, and deviation of the 1 to 10 numbers that we gave as an input. Now let's move to create a simple workflow, a Hello World workflow. How just is to demonstrate how we can create a Kepler workflow using the interface. So for a Hello World workflow, you need an input actor which will give string, so for the input actor, let's use a constant actor. To search a component, you can type a part of the string or the entire name of the actor if you know. So we see all the actors that are related to this string. So let's use drag and drop the constant actor to the workflow canvas. Now, if you want to modify the value of the actor, you can simply go here and as we want a hello world to display, let's type the value hello world. Now you want to display this hello world on the screen, so you need a display actor. So just I've typed a part of display string here and it gives all the actors that are associated with that string. To display this text, I'll just drag and drop display actor and connect the output port of input actor to the input port of display actor. Using you click on the input port and then drag to the output port. Now use the director. As this is a simple sequential workflow, we'll use the synchronous data flow director and to execute the workflow, let's run it. So this is a simple hello world workflow. In the similar way, you can drag and drop various existing Kepler components and create your own workflow and scale it using different actors. Let me quickly demonstrate MDCAD, the molecular dynamics drug discovery workflow. So I'll go to my workflow. So I have saved my workflows in this my workflow folder. You can right click and open it. So this is a module of the big molecular computer aided drug discovery workflow. It's GPU based molecular dynamics workflow. So you see different actors over here. This is a user configuration module. It's a composite actor. If you open the actor in a tab, you can see that it has a sub workflow inside it. And if you double click on it, users can edit the different parameters associated with this actor to change the configuration of the production simulation like temperature, simulation time step, etc. Another powerful actor that I would like to show you is the execution choice actor, which uses different execution, utilizing that you can execute your workflow on different platforms, like this production simulation. You can execute on local execution or Comet GPU cluster, which is an exceed resource, or a private GPU cluster, if you have some private GPU cluster on which you want to schedule it. So this is the internals of the workflow, but you can configure all the parameters from the graphical user interface. Like if you want to schedule the workflow on a private GPU cluster, you can change the target host to the cluster that you want to execute. If you want to run it on Comet, you can simply change the target host and run it. You can give other parameters such as which scheduler exceed resource or cluster is using. So I've already pre-configured this parameters by double clicking on this on the different parameters. You can execute the workflow using the run button. And this will submit. You just select the scheduler you want to submit to, and what's the how many number of jobs you want to submit it. The Kepler job submission sector will take care of submission it to the XE cluster, and as well as monitoring the status of the job. Let's run the workflow and see. So the job is being submitted to the cluster, and if you see this display actor, it will show the status of the job. It's in the wait state. It's remotely submitted to a GPU cluster, and it's in the queue right now. So with the help of job submission actors, you can submit the jobs and monitor the status of the workflow. Now I'll demonstrate the BLAST workflow. So this is the BLAST workflow, which has which has different execution choices. So BLAST algorithm basically compares the query file with the reference database and produces the alignment results. You have different execution choices. If you want to just do experimental run, you can use local execution to execute the same workflow on your local machine. If you want to use the map only or map reduce execution model, you can select using the drop down list and go into the workflow and configure your DDP actors for which execution engine you would like to choose, like Hadoop or Spark, to run this workflow. So I have selected the MapReduce choice and then selected Hadoop as my execution engine. So this will distribute the workflow on different cores on my local computer right now, but you can as well execute this workflow on EC2 or on Exceed nodes on Exceed cluster. So this is the alignment results that we found with the distributed workflow. Now let's see the reporting and the profiling interface of the Kepler. So if you go to the reporting interface, you'll see Workflow Run Manager. It logs all the previous run that you have executed. So from the provenance database, it queries all the previous runs that you have done. You can see the workflow name, the execution date of the workflow, and the duration it took, which user executed it. So with this, you can reproduce the workflows as it will save all the information about your previous run, like which variables you used, which actors were in the workflow, what was the time of execution, what was the duration each actor took. We can also see this in the profiling background. So if you So this is the profiling for the So this is the profiling for the BLAST Plus workflow we just ran. The workflow, the total time that workflow took was this much, and the different actors, the time that different actors took is also listed in this. Now let's see how we integrated Kepler to the Jupyter notebook. As you all know that Jupyter notebook is widely used by scientific communities this day. We integrated Kepler with Jupyter notebook so that you can stay in the notebook and scale up using the Kepler workflows. We designed Kepler magic function to run Kepler from the Jupyter notebook using command line style. To run the Kepler magic function, you can import Kepler magic function. Then these are the magic functions like kpconf, and you can declare the location of the Kepler on your machine using this command. You can, once you declare the location of the Kepler, next thing you have to declare the location of the workflow that you want to execute. To start the Kepler, you can, this is the magic function to start the Kepler function. within the Jupyter notebook. Once you start, so this will start the workflow that you specified in the previous step. It will execute the workflow, and then the outputs you can import the outputs of the workflow in the notebook. You can also import the reports that is generated by Kepler using the magic functions. So this is importing the MDCAD report that is generated by the Kepler. Here are the useful links to download Kepler and the link of the Biomedical Big Data Training Collaborative. Hope you enjoyed this session. Thank you. We can take up some questions if...
Thank you both very much. This was great. If people have questions, feel free to post them to the Slack channel so that our presenters can address them. I have a general question. Are there things you found that people trip over when they're first getting started that they should be aware of so they can avoid pitfalls of first-time use or something like that?
So we have yeah, so is there any, can you repeat the questions?
It was like, for someone getting started, are there obvious pitfalls that one might fall into, or is it anything you would advise people getting started to be cautious of?
To be cautious of, I think there's a learning curve, like many other scientific tools that come together. So the best way to start is really to go through that, invest in that 1 or 2 hours, go through the getting started guide listed in the documentation, and just have a familiarity with the environment. And sometimes we noticed, because we do a number of workflow trainings as well, when getting used to the clicks, click on a port and then link it to the other one, it can take some time, 5-10 minutes maybe, but someone showing quickly helps. The best model is, if there's a question, to ask that as quick as possible, because the solution is generally there, or, pretty quick actually. You would help, it would help to take advantage of the large community base to answer some of those questions. The other is we provide a number of workflows that are demonstration workflows. Kepler ships as a vanilla release. I strongly recommend vanilla release as in a base suite. Before switching to advanced functions or modules, I strongly recommend installing that and really going through the demo workflows to understand how the web services are being executed, or how you can connect to an external computational resource to execute something, and then switch to add provenance or fault tolerance or other modules, because it builds on knowledge of, a lot of that builds on the knowledge of the user interface and usability parts of Kepler.
How does one find out about the other training events or opportunities?
That's a good question. We provide training as a part of the SDSC Summer Institutes and National Center for Biomedical Resource Summer Institutes. We also we don't have one coming in the near future, but we sometimes announce those to Kepler users list and Exceed list. We run 2-day workshops that we call workflow-driven computing bootcamps. There, the main computing tool is Kepler. We also introduced some other workflow systems in the context of Kepler. But that's a 2-day-long hands-on Kepler training for scalable computing. We are hoping to have one in fall time frame again. We used to have them a couple of times a year. Now we switched to once a year. So we are planning to provide one. The other is we have actually a Kepler training on the Biomedical Big Data Training Collaborative. It's both on the slides and I think here in the Jupyter notebook. We can make this notebook available as well. It's an online environment. It's biobigdata.ucsd.edu that we built for collective data science training. And as a part of that, we put in a Kepler bootcamp set of slides, and there are some videos, especially the GPU-based molecular dynamics Workbench workflow you've seen. There's a whole class on that that shows how to use it and the science behind it and all that. We'll be extending those modules. We'll add more workflow training modules into the environment. And it's built as an open environment for anyone in the community to take advantage of and put training modules as well. So I would really appreciate if anybody has training modules, if they'd like to make them available on BBDTC, we'd be happy to talk and help you to set up your courses there.
Fantastic, thank you. I don't see any more questions on the Slack channel, so at this point I would like to thank Ilkay and Shweta for a great presentation. Thank you very much.
Thank you so much.
And you should see that we have the next 2 upcoming webinars in the next 2 weeks are on other workflow topics. May 3rd will be on high performance workflows with SwiftT, and then May 10th will be on radical cyber tools, an abstraction-based approach to scientific workflows. We encourage you, if you've watched either this live presentation or the recording subsequently, to complete the very short survey so we know what we're doing well and how we can continue to improve the webinar series. With that, we thank you, thank our presenters, and we'll see you next week. Thank you.
Thank you so much.